So, hi everybody. So it's nice to have you here for our first virtual in-person seminar. So, and today we have the honor to have Lorenz here with us, and he will tell us something about worldsheet correlators and AdS3. Okay.
Well, thanks very much, Falk, for the invitation, and thanks for being cool with me not being there. I'm sorry that I couldn't make the trip, but on the plus side, you can see my face. That's also something. All right, so yeah, please feel free, even though the setup might be unusual, to interrupt or ask questions at any time. Okay, so I will talk today about some recent work I did together with Andrea Day. We wrote 2 papers recently, and they're called something like 3- and 4-point functions. Okay, so what do we want to do? First of all, I think string theory and AdS is very interesting, and it's also very important for holography, and it's there is lots of progress, of course, but we're still not quite there where we want to be. So today I want to study one simple arena, and the simplest arena involving AdS, I think, is AdS3 with pure NS and S background flux, because in this case we can describe the string worldsheet theory using an SHET WZW model. There's a long history of doing that in the literature. And somehow there seems to be a general feeling that the SHET WZW model should be solvable, or is perhaps solved, or depending on who you ask. But I think so far there's only partial achievement of that goal. So in particular, there's, for instance, no closed form formula for the 3-point function or something like that. So that's basically what I want to do today. So we have some proposal for the 3-point function and the 4-point function of this model, and it turns out to be extremely interesting. So it's not just some horrendous formula, but first of all, the formula is kind of beautiful, I think, but it also involves some very intriguing mathematical structure. And so why are we doing that? It's not just for producing beautiful formulas, but it's also because if we understand string worldsheet theory good enough, we can just go and compute what is the spacetime 3-point function, what is the spacetime 4-point function, and so on. And you can just try to construct the spacetime CFT that is unknown in its full generality. You can try to compute it perturbatively what it is and try to prove that it's a consistent CFT, or try to find out what it is. So it's kind of reversing the usual logic of AdS CFT. Okay, so what's the difficulty? Why hasn't this been done like 20 years ago? So what we want to compute are holographic correlators in global AdS in full string theory. So you're probably used to drawing some kind of Witten diagrams. And if we go to string theory, we should fatten these Witten diagrams. And we get some worldsheet inside global AdS. So global AdS3 is just a hyperbolic 3-ball. So yeah, it's like a solid ball. And inside that, you have a 2-dimensional worldsheet. And here there's a sketch of that, and that is supposed to represent a 4-point function. And where you have the insertions of the vertex operators, the worldsheet touches the boundary or has like a singularity. And the very interesting thing about AdS3 is that you can have non-trivial winding around these insertions. So if you study flat space string theory, then there's just like a long tube. But since in AdS3, like you have like some boundary, so what you can actually have is like some winding of the worldsheet around that boundary. And it goes around, yeah, usually it's called spectral flow, but I will also sometimes say winding correlators. So you have these interesting correlators, and you see there's just one worldsheet, but it's somehow topologically non-trivial how it's embedded. And these winding types of correlators, they contain most of the interesting physics, I would claim, in this problem. So they are very rich and kind of interesting. Okay, and yeah, to advertise what mathematically will come in, you see that you have this worldsheet. Oops, you have this worldsheet and you have the boundary, and you see that the worldsheet kind of winds around the boundary. So what will come in a lot is that the worldsheet is sort of, you should think of as a covering space. So the worldsheet, like here, there are three, like if you have some boundary point and you think this worldsheet is close enough to the boundary, then there are like 3 pre-images of the boundary. So it's like a holomorphic cover of the boundary with which is branched over the insertion points. So that will come in a second. All right, so let me back up a little bit and explain you a bit about the Worldsheet CFD. So that's all like 30 years old or something. So first of all, I will restrict myself to bosonic string, and we will only work at genus 0, so you don't have to worry about any like picture changing and so on, all these kinds of things. So the symmetry algebra of Euclidean AdS3 is, well, of AdS3 is 2 copies of SL2R, but what the model we're actually studying is some analytic continuation of that on Euclidean AdS3. And so we are just, I mean, the symmetry algebra is essentially SL2C. So there's a different reality condition than what's for Lorenz's AdS. And so it's an alpha and Kac-Moody algebra. So it's basically an SL2R, but with some central extension. And everything that I'm going to say in this talk essentially is a consequence of this algebra. So this algebra knows it all. And this algebra will know about these covering maps and so on. So it's kind of fascinating that everything is inside this algebra. Okay, so now that we know the symmetry algebra, we should discuss what are the correlators that we want to compute. So we should stick some vertex operators in our Worldsheet theory and compute the correlator. Just as a very quick reminder, in flat space, if we do that, for instance, for a 4-point function, should think of the Worldsheet being something like this, and you have the asymptotic states that are the tubes. And the vertex operators in the Worldsheet are just plane waves, so they're just e to the IPx, for p being some momentum. And so they depend on this external momentum and the Worldsheet position. In AdS3, it's slightly more complicated, but also not that complicated. So the vertex operators, of course, are vertex operators, so they depend on the position z on the Worldsheet. But it's very, in the holographic setup, it's also convenient to parameterize them by a dual coordinate. So from the picture, so that's just the same picture as before, but in a sketch, the Worldsheet is touching the boundary at some point, like at some position. So there's also a boundary position. X for me is the position on the boundary sphere. And so every vertex operator has a position on the Worldsheet and on the boundary sphere. The idea is that now you're computing some correlator, you will integrate out the z positions by doing the modular space integral, and you remain with the x positions, and that will be your correlator in the dual CFT. Okay, so there are these two positions, which is maybe slightly unusual. And then there are some additional quantum numbers. So one quantum number is, or it's not really quantum number, but one number of this correlator, of this vertex operator is the winding. So you can have winding 0, 1, 2, 3, and so on. And of course, then you have some Worldsheet conformal weight, like you do in flat space. And since you have a second position, you also have a spacetime conformal weight. And these are independent in general. So you have 2 additional quantum numbers. And it's just also convenient to translate them into 2 different ones that are not independent. So to label the vertex operators by their spacetime conformal weight and by their Worldsheet spin. So there's an SL2R spin, like in any WGW model. And if you take the quadratic Casimir of that one, you essentially get the conformal weight. But since there's a spectral flow, it's slightly more complicated. But you don't have to worry about the details. I will just tell you the result in a few slides. Okay, so yeah, what these vertex operators, they're spectrally flowed. What it means technically is that they're not highest weight representations of this algebra. So it's not that you can take, say, all positive modes, annihilate this operator, all the 0 modes, transform it somehow, and all the negative modes give you descendant. It's a more complicated condition. And that's essentially why computing these correlators is hard, because you can't, like, in general, if you have some kind of descendants, then usually you can always reduce it to the primaries. But here, since like the condition is more complicated, you can do it, it turns out, but it's much more complicated. Then one important ingredient, what I will say, is that the unflowed sector, by which I mean if you compute a correlator where all the vertex operators have w equal to 0, they're all non-winding, that is completely solved. So there are old papers by Jörg Teschner where he gives a complete solution of that problem. By complete solution, I mean there's a proposal for the 3-point function, like there is in Liouville theory. There's a 3-point function that is very, very similar to Liouville theory. And then you can do a conformal block expansion to get the 4-point function and so on. And there are some very partial results also about these some flowed correlators. So for instance, a 3-point function with 0, 0, 1 or something like that for the W's. Okay, so basically our first goal in this talk is to get some formula for all the correlators. And as a technical tool, because it will turn out to be much easier that way, is it's easier to introduce a third coordinate. That third coordinate, I don't know of any physical interpretation, at least any straightforward one. So it will just be a technical tool. And it's just that if you take this vertex operator, but by the way, there's an H and H bar. I hope that there's always everything is that exists for left moving also exists for right moving. I mostly focus on the left movers. So, and you can take this vertex operator and just do this kind of integral transform, kind of Fourier transform. It's just more convenient to have this third coordinate around. But you can always go back and forth. So what I actually now want to compute are these kind of correlators. And you already see that if you take some 4-point function or something, you will have something like 20 parameters. So it's kind of, it's not super difficult, but this problem is just there are so many parameters. So we will just use symmetries to constrain the answer. There's nothing really intelligent we do. There's just imposing all the constraints from the algebra and so on, and then making some educated guess what the result should be. And since we're doing that by brute force, we will restrict to n at most 4. So I will consider at most a 4-point function on GLS 0. So I will quickly tell you what are all the constraints, but I will not go through and tell you what precisely they do, but I will then go to the final answer. So this easiest type of constraints are word identities. You should know them in CFT. You have like some conformal group, and that conformal group allows you to put 3 coordinates to whatever you want. Since here you have 2 conformal groups, namely the one on the worldsheet and the one in the spacetime, one transforms the z coordinate and one transforms the x coordinate. You can set 3 of the x's and 3 of the z's to whatever you want. And let's take 0, 1, infinity. So that means for the 3-point function, we already win and have all the x and z dependence. For the 4-point function, we have 2 cross ratios. But that's not the end of the story, because we have affine symmetry, not just global symmetry. That's why this NS and S background is so nice. And because of that affine symmetry, there are something we call local word identities that are stronger than these global word identities that restrict the answer further. And these are the complicated ones, and they depend on the spectral flow and so on. So, and also they're so complicated that we can only compute them case by case. So you can say to me, I want the local word identities for spectral flow 557, and I throw the Mathematica and wait 1 hour or something, and then I can give them to you. But so they're kind of complicated. And finally, there will be also more types of word identities. So one is the Knižník-Samologikov equation that comes from the construction of the energy momentum tensor. And for special choice of spins, you also have null vector decoupling equations. So as I said, don't worry about it, just if you're interested in the technical details. So now I have to explain you the mathematical input that I already hinted at, and then I show you the result. So the mathematical inputs are branch coverings, and they will appear everywhere in the solution of all these constraints. So what is a branch cover? It's nothing else than a holomorphic map. So it's a holomorphic map from the 2 sphere, from the Riemann sphere to itself. And the one Riemann sphere, this Riemann sphere you should think of as the worldsheet. This Riemann sphere you should think of as the boundary of AdS3. And it's a holomorphic map, and it has finitely many ramification points, which means that there are finitely many points, finitely many critical points, let's put it like that, where the derivative is 0. Okay, so the derivative at these points is 0, so we can make some Taylor expansion. And it says basically if you, so first of all, this gamma of zi should map to xi. So that zi, you should think of the position of the vertex operator on the worldsheet. Xi you should think of as the position on the boundary, and these positions should map to each other. And then there are terms missing in this Taylor expansion because it's a branch cover. And then so the first term that is there is this zeta minus zi to the wi with some coefficient that won't matter. And then you can go on. But and we will have an example on the next slide. So that's and there are no other critical points of this map. So it's a very simple thing. I hope I didn't confuse you by making it complicated. So, but one super important fact is that if you give me some random collections of xi's and zi's and wi's, so meaning some points where gamma is critical and gamma of zi should map to xi, and here it's critical of order wi, then in general you won't be able to give a covering map. So it's a very strong condition because of holomorphicity. And you can kind of easily convince yourself or compute using Riemann-Roch theorem that the existence of such a map puts you n-3 constraints on the set of xi's and zi's. So that means basically all the cross ratios, say the x cross ratios, are fixed in terms of the z cross ratios up to discrete choices. Okay, one other thing is that also the degree of the map is fixed. So the degree is how many pre-images do you have. So for instance, in the very first slide, we had 3 sheets. That would be the degree of them. And it's computed by some very simple topological formula, which is this Riemann-Hurwitz formula. It doesn't really matter, it's just that it's fixed. Okay, so let's do an example and see what this is about. So let's find the branch covering map for these choices of W's. And we also make some choice of X and Z, and we keep the most general. So we can always do this kind of Mobius transformation. So we can put 3 X's and Z's to 0, 1, infinity. And the last 2 are free. So that's my data. Now we try to find a covering map. Using this Riemann-Hurwitz formula, you can immediately see that this covering map has degree 2, provided it exists. So that means, so let's write down the most general degree 2 map from the sphere to the sphere. It takes this form. Okay, it's a rational function of degree 2. And now there are basically 5 degrees of freedom in here. One's redundant. So let's just use them to fix, no, we don't need that. Use that to fix all the constraints. So you immediately find, if you impose these Taylor conditions at Z1, Z2, Z3, that gamma has to be of that form. So, and you can check, that's it's in this box here, that gamma of zeta near 0 is minus zeta squared. So it's of order 2, and also 0 maps to 0. And gamma of zeta is 1 plus something of order 2. So 1 maps to 1 and a branch point of order 2, which matches with, because we chose them to be 2 and 2. And then W3, W4, we chose to be 1. So 3 is slightly special because it's infinity, but that means infinity maps to infinity and so order 1. Okay, but the only thing we haven't done is to impose the Taylor expansion at Z4, which is Z. So gamma of Z should also map to X, right? That's the only thing we haven't imposed. So you get a condition that relates Z and X. And so you see you were not free to choose Z and X in whatever way you want, because in general, you can't make a covering map. But only when Z and X, well, you can satisfy this condition, can you find a covering map, okay? So that sounds kind of stupid, but it's extremely important for what follows. So now out of this, we can build a polynomial for any choices of ramification indices. There's such a polynomial that tells me the relation between Z and X, the 2 cross ratios for 4 points. So we just computed that polynomial in the case 2, 2, 1, 1. That was the example we just had. And we computed that polynomial is this. I will just put a very simple prefactor, and you don't have to worry about it. It's just that this slide is correct, but just otherwise forget about it. Okay, it won't matter for the following. And but you can now come up with this polynomial for any choices of W's. So for instance, I wrote one example here, 2, 2, 3, 3. This polynomial would be just this thing. And so the way we computed on the slide before is not very efficient, but there is an efficient algorithm to compute this. Okay, maybe I should also have mentioned this very simplest example, like that everyone is on the same page. So if you put all the ramification indices to 1, then this means you're searching for a map that is nowhere ramified, because like it's ramification index of order 1. And so this is a Mobius transformation. And you know that on the Mobius transformation, the cross ratio has to be preserved. So this means the very simplest example that maybe I should have mentioned is that P1111 is just Z minus X. Okay, because the cross ratios should be the same. Okay, so this is this P polynomial. Because of this Riemann-Hurwitz formula, it's only defined if the sum of W's is even, but it doesn't really matter. And what's kind of amazing is that these polynomials satisfy 1 bazillion identities that I won't bother you writing down, because there are like 10 pages of identities. And you need all of them for this solution that will come to be consistent somehow. And I have also not seen anything like that studied in the math literature, so it would be kind of interesting to explore that further. There has to be something behind that. So all these identities we sort of check numerically, but I have no idea how to prove them. Okay, so now I need to make one more definition and then we're done. So first of all, one thing is that a solution will only exist to all these constraints if there is some kind of inequality on this W satisfied. Basically, this inequality says that you can't make some winding string of, like, let's say winding number 1 into winding number 1,000,000 or something. There's a kind of conservation of winding number, so that sort of the sums of some group of winding number cannot be bigger than the last one. Yes. Okay. And okay, finally, I define one quantity that seems also kind of mysterious now, but I define xi for I any subset of 1, 2, 3, 4. So that's still for a 4-point function. And it's just a combination of these PWs that we just saw. So you're free to decode that formula, but let me just explain you an example. So if the subset is the empty set, then it will just be PW, this polynomial we saw. If the subset is, let's say, 3, okay, this is just a set 3, then what you should do is to take this P polynomial. Sorry, this is kind of technical and boring, I know, but it will get interesting on the next slide, I promise. So you should take this P polynomial and shift the third W up by 1, and you combine it with the P polynomial where you shift the third W down by 1. Sorry, that's W2. And you put it Y3. And here I wrote the example of x12. It means you take this P, so there are 4 terms. In general, there are 2 to the number of elements in the set terms. And you take the first 2 W's, you shift up by 1. Then you put the Y1 and shift this down by 1. You put the Y2 here and shift this down by 1. And you put Y1, Y2, and you shift both down by 1. Okay, and now you should be able to see that if you put like 3 subsets, then there are 8 terms and so on. Okay, so now finally, it's getting maybe interesting. So here's a conjecture, and I want to explain it a little bit for what these correlators should be. So this is basically a proposal what the most general 4-point function is. And for the 3-point function, it simplifies. Okay, there are 2 different cases. It depends on whether the sum of the W's that enter in this correlator is even or odd. And the formulas kind of look similar, but let me just talk about the even one. The odd one is very similar. And it takes a very simple form once you make this X definition that we made on the previous slide. So first of all, it's expressed in terms of this integral transform that we defined in the beginning. Just to recall, so we had vertex operators that depended on the Worldsheet position, the spacetime position, the spacetime conformal weight, the SL2R spin, and the winding. And I told you that it's useful to do an integral transform on these H's, and that is this integral transform. So what's written, like the remainder of the formula, is the correlator in this Y space. Okay, and the Y space correlator is sort of simple. So it has some prefactor that is in terms of these capital X's. And finally, you get a correlator. So it sounds like I'm cheating because I'm expressing one correlator in terms of another correlator, but you get a correlator here. And the very important thing is that this correlator is the same one that appears here, but it is in the unflowed sector. So all the W's have been put to 0. And you remember this one was solved by Teschner. So this quantity that enters here is actually known. If this would be the 3-point function, then there's a very explicit formula in terms of like epsilon functions and so on, like in derivative theory. For the 4-point function, this has to be expressed in terms of conformal blockage. But this object I assume to be known. But it's evaluated at a different point. So it's evaluated at this strange type of cross ratio. But remember, these capital Xij's are nothing like Xi minus Xj, but there's weird combinations of these P's with Y's. And similarly, also here, the prefactors, they look like, so actually the whole thing looks like a CFT 4-point function, where this capital Xij would be Xi minus Xj, usually. Okay, if I wouldn't have told you what the definition of Xij is, you would have suspected Xij should be something like Xi minus Xj, right? Because then this is exactly what we have in a CFT 4-point function where we 3 points to special positions. What we should do is to put these prefactors. The only exception to that is that you also have this X empty set appearing. So that you usually don't have in a CFT. But it's kind of intriguing to me that you get exactly the same form as in the usual solution of word identities, but instead of these xij's being differences of coordinates, you get them to be these weird combinations of these p polynomials. Okay, so that's the formula. Okay, the main takeaway from this is that the unfloat correlators, that is this one, give you the float ones for free. There's no additional input that you need. Well, there is additional input, but no CFT input. Like the only input that you need is kind of geometry, because you need to analyze these branch covers and produce these p polynomials. And then you just stick them inside, and then it's some kind of integral transform that transforms the unfloat correlator into the float one. And also this now basically gives a full solution of the model. So in particular, it gives you, for the 3-point function, it gives you a closed form formula for what are all the 3-point function of primary fields. You could also start doing descendants and so on. But okay. So let's discuss some more properties that these correlators have. So they have some weird properties. And the first one maybe is that there are more singularities in these correlators than you might think. So usually if you have a CFT, then you get a singularity in the correlator whenever two vertex operators collide. So first of all, in this case, you have more coordinates. You have these Worldsheet coordinates, but also the spacetime coordinates. And the vertex operator can either collide on the Worldsheet or in spacetime. So that means you have all these conditions. You get a singularity. But, so that's not particularly interesting. What's interesting is that you also have singularities that are somewhere in the middle of modular space, where no vertex operator collides. These are singularities that occur whenever PW is 0. So there are actually even more than that, but let me focus on those. So when PW is 0, so remember that was this polynomial. If it's 0, it tells you there is a covering map from the worldsheet to the boundary. That was the definition of PW. And if it's, and that occurs somewhere in the middle of modular space. Let's just copy the previous one that we like, the z squared minus 2zx. So just that we have an example, minus 2zx plus x. So that was the example we calculated before. If this is 0, then there's this covering map of degree 2 of ramification indices 2, 2, 1, 1. And it's somewhere in the middle of modular space. Like for instance, if you choose x some random number, then z, there would be 2z satisfying this, and they're also random, kind of random numbers. They're not 0, 1, or infinity. Okay, and also the number of z's that satisfy that, like if you go higher in the w's, there will be more and more such z's. So there will be more and more such singularities in modular space. What's also interesting is that the correlator, so the formula I showed you before was kind of complicated. It involved these 4 integrals over y's and all kind of p polynomials and so on. But if you expand that formula for z close to z star, where z star is a solution of PW being 0, like imagine fixing x and then fix some solution. If you expand around that solution, you get actually a much easier answer that you can express in terms of other things that I didn't want to write down, but you get much easier things, and then you get the singularity. So you see very explicitly there's some kind of singularity. And so it's singular whenever like this exponent is negative. If it's positive, then of course there's no singularity. Okay, so why does this happen? So this is actually not something new. That was known that something like that should happen. It actually already happens in the unfloat sector. The reason is that if PW is 0, then by definition there is this covering map that the worldsheet can cover the boundary holomorphically. Because of that, if you look at the action of the model and you write down the path integral, then you see that when there is such a, if there's such a map, you should think of such a map as like a worldsheet instanton. So it has like an action that doesn't grow very fast if you take the worldsheet outwards. And because of that, the path integral, so there's one mode in the path integral that you should integrate over, which is the radial position of the worldsheet. So you should integrate over all the moduli of the worldsheet. So in particular, one is taking the worldsheet outward. And the action depends only very weakly on that. direction. So if you compute the path integral, then it turns out actually that it can diverge if you take it outward, and it diverges precisely for a condition like this. So like it depends on what you choose for the spins, whether it diverges or converges. And you see that there's like one critical choice of spins where the path integral starts to diverge. And that is basically the explanation, and that divergence you see in the correlator. So that is the explanation of Malthus and Noguri, why this happens. So it's kind of, you should really think of these kind of being worldsheet instantons, and you see them here at tree level in the string worldsheet computation. Okay, I'm actually doing very well on time, so you should be really free to interrupt me if you have questions. Okay, then we can go further than that and compute actually the full string correlator. Right now we just discussed worldsheet correlators. We haven't done string theory yet. So if you want to do string theory, then all you need to do is to integrate over the moduli, which for a 4-point function is just a z cross ratio. And so we already saw that there's a singularity. And one interesting thing is that if you tune the exponent of the singularity, let me go back to it. You tune this exponent to be close to, so first of all, if it's bigger than -1, it converges, and the singularity does nothing particularly spectacular. But if you tune this exponent to be close to -1, if you put it exactly -1, then the integral over moduli space would diverge, right? And so the presence of this exponent tells you that the string correlator, after you did the z integral, should have a pole in the spins, and this pole goes roughly like this. So you expect something like this, ji minus k plus 1. So it tells you if this sum over ji minus k is -1, then you should get a pole. So you should get something like this. And what you can do is actually compute the residue. So, and that is, it turns out to be a very, like many things, miraculously simplified. Okay, it's actually even easier to compute a slightly different condition on the spins. So this condition is related to the previous one if you swap all the spins from j to 1 minus j, which is reflection symmetry in the model. So it's just, it will give a simpler result, but they are equivalent vertex operators because there's a reflection symmetry that relates j and 1 minus j. They have the same Casimir. Don't worry about it. So, okay, so we can compute this residue. Let's go. So we have to put some normalization of the string path integral. We have to integrate over the worldsheet position, and we put our worldsheet correlator. And since we're doing string theory now, we can also imagine that we have something like AdS3 times some internal space. So we need to have that to get the critical dimension, which for the bosonic string is 26. So I put here some internal vertex operators. Okay, so now we do this integral. And what happens is that, so we tune the exponent, so it's dominated by the singularity. And so actually this whole integral will collapse to an integral to a sum over all these singularities. And now we have to evaluate this, the integrand close to the singularities. And it turns out you can do that very explicitly. And you see that in this formula, first of all, there's no y integral. So this integral over y you can just do, and it's very easy. And that's only because we are close to the singularities. And then you go through some magic identities and you find this result. So let me explain you. First of all, these first two terms are very easy. They're just the position to some power and 1 minus position to some power. So it's just a free boson correlator. There's nothing strange about that. Here, there's some normalization. Fine. Also nothing spectacular. So the second line is more interesting. What you get here, these A's actually appeared in the very beginning of the talk, but I haven't actually mentioned them. So these A appeared in the covering map. Namely, the condition in the covering map was that gamma of zeta is xi plus ai zeta minus zi to the wi plus higher order. So these ai's are the a of the covering map. Because by definition, so if we're in one of these terms, it means z star solves the equation that p of x star z star is 0. So, and that by definition means there is a covering map. And of that covering map, you can compute what these AIs are. And they appear here in this second line. And similarly, there's a pi, what we call pi appearing. Pi is the product of all the residues of the covering map. Anyway, but this is like stuff that is determined by the covering map. And finally, of course, the internal correlator, we don't know what it is, but it's still there. And it's evaluated now at zi star and no longer at zi. Okay, that seems like a boring formula perhaps, but let's look at it in detail. And first of all, we notice that there's kind of this free boson part to it. And it really looks like free boson because you also have these quadratic exponents. And then finally, and then in the second line, you have these A's that come from doing some covering now. And it turns out that actually exactly the structure appears in symmetric product orbifold CFTs. So if you look at a symmetric product orbifold, in this case, you need a free boson with a particular background charge, and you combine it with X, where X is the internal space CFT. So let's assume we started with something like AdS3 times X, then there's some worldsheet CFT that describes X, and we put it just here. And of that, you take the symmetric orbifold, which means you take n copies of that theory, and you divide out by the symmetric group action that permutes these copies. So this is an orbifold, so there will be an untwisted sector and a twisted sector. In particular, the twisted sectors of a symmetric orbifold are labeled by conjugacy classes of the symmetric group, which are labeled by like cycle types. But if we focus on like the single particle part, so we're focusing on just single particle string correlators, then the twisted sectors are just labeled by single integer, which is basically a permutation up to length W. So there are twisted sectors of length W, and you can compute their correlators. And the claim is that these correlators precisely match with the formula that we saw on the previous slide. So slightly more detail, how does the matching go? So you should identify the momentum of the free boson, like so. So this alpha I is the standard notation that you have in Liouville theory, for instance. And then the free part of the correlator is just expressed like that. So that was this, yeah. And we also had, remember, this only worked, this computation, when we had some condition on these J's. And so the condition on the J's translates immediately to momentum conservation. So that also works. And then, of course, you can do the more refined computation and check that you actually get exactly the same result. So with that, you can now check that our computation basically gives a direct proof of something that has been around in the literature for some while, but it was not super clear how it should go, is that this singularity in the correlator should be described by some kind of symmetric orbifold of something. And it turns out to be this. Yeah, so I think I see that Emil is actually in the audience. So Emil has two very recent papers where they, in some other limits, say that the full dual CFT is actually this, where you turn on some additional particular twist 2 operator. And it seems like you can make that work also on the level on the correlators in general. So that's work in progress. And so I'm kind of excited about this. And hopefully we'll have some nice story about that, but stay tuned about it. Okay, so finally, in my last like 10-15 minutes, I want to address a particular limit of this, what we discussed so far. So the interesting limit that you can take is where there's actually a description of the symmetric orbifold that is exact. So right now we just matched one residue in these correlators with the symmetric orbifold, and then you should do some deformation of the symmetric orbifold to get the exact, the correct answer. But there's a particular case where this symmetric orbifold on the nose is already exact. And this particular case is superstring theory in AdS3 as 3T4. So now we need to go to superstring for k to 1. So k was this like amount of an SNS flux in the background that appeared in the appeared as central extension in the affine algebra. And k to 1 in superstring corresponds to k to 3 in the bosonic string. So there's always this kind of small shift. So roughly speaking, k to 1, you should think of being very small tension. So if you put k to 1, then the target space is very small compared with the string. So the string is like very big and like almost glued to the boundary. So it turns out that if you're in this case, then it's nice because you have even more constraints. So there are some additional null vector constraints that I don't want to go into, but these null vector constraints give you even more constraints in the correlate. And now you might think, how can that be? Because we already found the full answer. So there is a slight surprise here. first of all, these constraints tell you there's actually that only spins 1/2 are allowed. Before we had the spins j to be anything we wanted, and now only j to 1/2 is allowed. But j to 1/2 is a kind of special because you see before we had the condition that if the sum of j's is 5 minus k, then something special should happen. But now the sum of spins, they're all 1/2, so it's 2. But 2 is 5 minus 3, which is 5 minus k, because you should take k to 3 in these formulas. So it seems like you would always sit on this pole. So we discussed this pole before, and we can compute the residue. But here we can not choose our spins to be whatever we want. So we're just sitting on the pole all the time. We don't have choice. So it seems like we just get nonsense. But it turns out that the nature of the singularity actually also changes and exactly compensates for this. So to see this, let's write down the answer of our formula for the 4-point function. Let's write it down in this special case where we put all the j's to 1/2 and we put k to 3. In this case, you get these prefactors of xij's and x empty set. They just simplify and all exponents are -1. And here you still have this cross ratio. So that whole formula collapsed to that. Of course, I forgot here absolute value squared. Okay, but now you see that how things could change. Namely, x to the -1 is basically as good as a delta function. Why do I say that? I mean, because the two things satisfy the same differential equation. And all the constraints are in form of differential equations. So you see that if you take a derivative of 1 over x times x, then you get -1 over x. But if you take derivative of delta function times x, you get minus delta function. So the two things satisfy the same differential equation. That means that if you have these all these constraints, that actually there is a second solution. Namely, the solution where you replace x to the -1 by a delta function. That won't change, like all the differential equations that were satisfied before are still satisfied now with the delta function. And so in general, you might worry that there are these two solutions, but you see in general, you could just smoothly vary this exponent here. And only if this exponent is a negative integer can you have such a delta function solution. So this delta function solution can only be possible in this tensionless limit where this exponent is frozen to be -1. And it turns out that in this tensionless limit, the delta function solution is the only solution that is compatible with all the constraints, because there were even more constraints in this case. And that's kind of, first of all, it's very strange that you have a CFT where the correlators are delta function localized. So this correlator is mostly 0, except if x and z satisfy some special relation, then you get this delta function. So it's kind of a very strange CFT. And so now if we do the string integral over the moduli space of Riemann surfaces, just over z, then instead of being dominated by the singularity or something like that, like before, it actually receives only contributions from the singularity because of this delta function. So it only receives contribution from points where this x empty set, which was just PW0. And so our computation that we did before exactly goes through, with the only exception that we're no longer computing the residue of the answer, but we're computing actually the exact answer. We're computing the exact string coordinator. And so this tells you that the string coordinator is exactly as symmetrical we thought. Of course, there's some kind of subtleties that because we're actually doing the superstring now, so you have to do picture changing and so on. But the moral is that one. So if you
can I
yes.
ask a question here? So
Please.
this x inverse being replaced by a delta function, does that mean there's a suppression of some sort of fluctuations, or that some kind of classical solution is becoming exact? I mean, how do you think about it?
I think about it, yeah, I think about it that the classical solution is, so the worldsheet is kind of pinned to the boundary. And so if you want, like it can't fluctuate anymore because it takes like infinite amount of energy to go back in. So so because of that, since it's pinned to the boundary, it can only be pinned somewhere where you have like this only costs you a finite amount of action, which basically means that PW has to be 0. So that's one way of seeing it sort of semi-classically. But I don't know of a super honest way to see it semi-classically. So it's all kind of hand wavy.
Yeah, I guess what I was wondering was whether Yeah, that you could say somehow the strings are somehow more pushed out to the, is that your intuition, that they're somehow more
that's my
concentrated at the
intuition.
boundary than usual?
Yeah. Actually, if you look at the classical solutions, you can actually see that they have like an, so usually like the variables that you have in the classical sigma model are usually called gamma, gamma bar, and phi. And you can see that phi is formally always infinite in this k to 1 limit, because it turns out that gamma and gamma bar become holomorphic. And if they're holomorphic, then phi gets pushed out to infinity. So you can see that semi-classically.
Okay. I see. And so then these, okay, I understand. So you say, if you look at the vertex operators in the X representation, there's sort of a bulk to boundary propagator, and you say that's being evaluated where the bulk is being taken to the boundary.
Yeah.
So it becomes a delta function where gamma equals X.
Right, yes.
Okay, great, thank you.
Yeah, thanks. Any other questions while we're at it?
Yeah, Lorenz, may oh.
Yes. I can't hear you now. The whole room is muted. Still can't hear you.
We can hear you.
Yeah, now I can hear you as well.
Yeah, can you hear us? Awesome.
Yes.
I'm sorry for that. So that was some kind of feedback. What I wanted to ask you, when I remember correctly, so the top coupling is normally indirect proportional to the tension of the spring, right? So when you take the tensionless limit, the top coupling in the CFT should become very, very weak. So that means you go there to some kind of classical limit. Can you see something like this behavior? So do you get a weakly coupled CFT then?
I mean, yes, you get. I mean, it's a CF. It's not. You're probably more thinking about something like super MMOs.
Yeah, I was exactly. This was my example. Yeah. For
yeah.
sure.
So in this case, I mean, depending who you ask, people will tell you that the symmetric product orbifolds are free, almost free, or something like that. Yeah. So essentially, they're free. I mean, it's an orbifold of a free theory. So the moral analog is the weakly coupled.
Okay, that's good, because I was confused by the orbifold, because normally orbifold theories are the other thing than free, right? Because you have this orbifold point, so where you have some kind of singularity and so on. But here you say it's more like you would take when you take the line and then you make an orbifold to get the boson on the circle.
Yeah, that's it's morely. I mean, it's like a. So the only non-trivial thing about this theory is that are the twisted sectors. So you have to compute twisted sector correlators, yeah. And the kind of standard procedure is let me explain that, because the next slide anyway is conclusion. So if you have some correlators of twisted sectors, then you can think of, so they're twisted. So if you go around them, there's a monodromy. So there are several sheets that. So for instance, like let's say X1 goes to X2. So these are two copies in the symmetric orbifold. Let's say this twisted sector exchanges them. So that means you can think of X1 and X2 being two sheets.
Yeah.
And then what the standard procedure is that you lift that correlator to like a covering space, where like instead of computing the correlator on the original space, you compute it on the space of X1, X2. So these are two sheets that meet there. And then you get a correlator in the original CFT, but on a different surface. And that surface might be higher genus, or it might be more complicated. So actually the genus of that surface is the genus expansion of the symmetric orbifold. And also, yeah, and if you go to that surface, you pick up some conformal factors because you're changing the metric. And these conformal factors are precisely these here. So this is how these factors come about, because these are basically the derivatives of the map the conformal transformation.
And the N you find is the same as the large in limit in super young nodes, right? So,
yeah. I mean, the details are different, but for instance, here the central charge is proportional to n, whereas in super young nodes it's n squared. But like this, basically, what you would call in super young nodes squared n squared, you should think of being n, morely.
One more thing. So have you also thought about the limit where k goes to infinite? So so where k is very, very large. So the large level limit. Is there anything happening there?
Yeah. So this limit also connects to many things we know. So first of all, large k, you would go to supergravity, and yeah, even depends on how you think how you scale things. Like it goes to flat space eventually. Basically, the string becomes small to AdS compared to AdS. So, well, in my kind of story, that limit is sort of not interesting because the twisted sectors or these spectrally flowed vertex operators, their conformal dimension scales with k. So if you take k to infinity, then they just decouple and go away. So essentially, if you send k to infinity, then you have nothing to, I mean, then there's nothing new in this story.
It's like winding modes on a circle, right? So when you make the circle very, very big, the winding modes become very heavy, and so they are not relevant anymore.
Essentially, yes. So these are not literally winding modes like these winding modes. So in particular, these winding modes here, these spectrally flowed sectors, they're not topologically protected. So if you look at the previous, like at the beginning picture, then you see that there's actually nothing topological that would like preserve this winding in some sense. There's nothing it winds around. So you might also wonder why this is even a well-defined quantity. It turns out it is, but it's not literally a topological sector. But yeah, it's similar.
Yeah, okay, thank you. That was very helpful.
Yeah. So one thing, yeah, I mean, if you do this limit, then yeah, you just remain with the supergravity modes essentially. Okay, other questions? If not, let me conclude, and then maybe we can have more questions then. So I have just a brief summary. So what I showed you in this talk is a full conjectural Stowe solution of this model. So it's technically called H3+, which is the Euclidean analytic continuation of the TSL2R WZW model, including spectral flow. At the moment, we are bound to at most 4-point functions on the sphere, but I think the general lesson should generalize. And the general lesson was that knowing the unflowed sector, the unflowed correlators, and knowing about the geometry of all the branch covers, you can write down a formula for all the correlators involving spectral flow. And these Worldsheet correlators that you get, they have a very interesting singularity structure that depends on all these covering map geometry and so on. And near some singularity that you get, you can compute the full string correlator very explicitly, and it becomes a correlator of this CFT. And finally, I showed you this special case of the tensionless limit. In this tensionless limit, instead of having like power-like singularities, you have delta function-like singularities. And you can just do the modular space integral is trivial and reduces to sum over these delta functions. And you get this relation with the symmetric orbifold that just becomes exact. All right, that's it from me. Thank you very much for listening.
Can I ask a general question?
Please.
Yeah. Now, this work teaches us lessons about how to deal with strings in AdS background. So it's very valuable in that sense, because we all know it's very difficult to do string theory in AdS background. But if I consider higher dimensional AdS spaces, string theory, let's say in AdS4, AdS5 cross S5, let's say, how much can we learn from this for the case of AdS5? Are there any important points we can extract from this?
I think the truthful answer is that you can't learn a lot about AdS5. I mean, I don't know anything you can learn. Well, let me just point out that the spectral flow is a phenomenon that only exists for AdS3. I don't know of any analog in AdS5. You can already see from the geometry. I mean, if your AdS is 5-dimensional, then there's just no winding you can have. Like the Worldsheet can't wind. Maybe if you consider something like D-branes on AdS5. So there's no, like, so that means like essentially everything here is not relevant for AdS5. And
perturbative
still in AdS5 we have,
treatment and perturbative treatment of AdS5 is useless, basically. Would you say? I mean, and if so, why is that?
Perturbative in alpha prime, you mean?
In the sense that yes, I mean yes.
It's useless. I wouldn't say it's useless. I mean, it's very useful. But AdS5, of course, is much harder because it has pure Ramond background. So you have to do, you can't do the RNS superstring. You have to do something like pure spin error. So that, like, also the technology is just very different. And you have, from a Worldsheet CFD point of view, you have almost no symmetry. You just have the PSU 2,2/4, and that's it. You don't have something like an affine symmetry. So that's why, from a Worldsheet point of view, AdS5 times S5 is almost hopeless to do. Exactly. I think. And
tensionless limit is no help either, would you say?
Well, there is actually recent conjecture by Gabadier-Gopakumar, where they looked at free YAG-mills, free super YAG-mills, and they looked at the spectrum, and they asked themselves, maybe there's a simple, perhaps almost free Worldsheet theory that reproduces that spectrum. And sort of like, let's just forget about the mid-Zeitlin superstring and so on, but let's just try to get any CFT. And they make some proposal. There are still some kinds of, there's some things that are still missing, but they have a proposal on how to reproduce free super YAG-mills from the Worldsheet, which, if it works out, it's great. So, but it has nothing to do with all the conventional string theory formulations on AdS5.
When was this work done? Can you?
It was this year. So it's called something like the free string dual of NE24 super YAG-mills. Something.
Okay,
like
thank you.
Two papers.
Thank you very much.
Yeah, are there any other questions here from the audience or from the virtual participants? Okay. Yes, please. Go ahead.
Are you able to hear me?
I can hear you, but not very well. If you could speak up a bit.
Yeah, or can you hear me now?
Yes, it's better. Thanks.
Yeah, so I mean, I have a very naive question. So I know that I think people in the Bootstrap community, they try to construct the gap in the AdS3 bulk used by studying the boundary CFT and try to constrain the gap using numerical techniques. So does your work shed any light on that?
I'm afraid also the honest answer is not really, because the problem is, again, that these are very stringy correlator, and the gap you're thinking about is rather, I mean, it's not of stringy nature, right? You're thinking about some, I mean, probably you want some kind of semi-classical gravity in the bulk, and that's what these people are trying to do. But these stringy, I mean, these winding correlators, they have order k. Maybe I should clarify the order of magnitude that's involved. So there, the dimension of these winding modes are of order k, which is still much less than the central charge, but it's still very large in supergravity. So there's a hierarchy of order 1, order k, and then order central charge. Order central charge is something like n times k, where n is the n of the symmetrical before. So k doesn't scale with the central charge. Yeah, so that's why I think it's probably not super useful for constraining these kind of gap. One thing I should also, in context of Bootstrap, people in Bootstrap are usually thinking of CFTs with compact target space or discrete spectrum, whereas this spacetime CFT, or this string theory on NSNS background, actually has a continuum in the spectrum. So that's sometimes known as the long string. So, and the reason for that is that you can choose this spin. So I haven't discussed this, but the spin you can choose either in the real numbers, and then you get discrete representations, or you can choose it in principal continuous series. And if you choose it in the principal continuous series, you land on a continuum spectrum in spacetime. And because of that, essentially, like, usually these kind of CFTs are not captured by the Bootstrap program.
Okay, very good. So, and there are no.
Can I ask one more question? Is there an interesting? Can you see any additional structure or pathologies that appear when you try to extrapolate to large windings?
Extrapolate in what? So these formulas are exact in the winding, or what do you?
Well, right, the symmetric product, you know, as you well know, the symmetric product is usually not quite what you get from the worldsheet. Worldsheet is some kind of grand canonical ensemble of different orders of symmetric product.
Yeah.
So if you tried to fix the order of the symmetric product, then you have to do a Legendre transform of your answers.
Yes.
And then the question becomes, okay, if the winding becomes of the same order as the order of the symmetric product, is there anything in your formulas that you know, changes, or is that only going to appear when you start including the Z2 twist interaction?
I think even with the Z2 twist interaction, so my computations until now is show that if you put the Z2 twist interaction, then at least in like fourth order in perturbation theory, you just get, for the 3-point function, you get this result. But what of course should happen if you do something like a 1/n corrections, I'm not sure whether you even see it perturbatively, but at some point in the 1/n corrections, you should of course see that W cannot become larger than n. But
Right.
here, this is all treatable. But I think the Z2 twist interaction doesn't change that picture. Do you? I mean, you thought about it more than I.
Not yet.
Okay, very good. Thank you very much. So I stopped the recording. First,
Thank you all.
the recording.